this algorithm, there are some variants of that and all that, but that time I told you that actually this mean square estimation is a more general mathematical problem that of computing orthogonal projection of some element on a space spanned by some other elements. Okay. So, we need to build upon that, because the general adaptive filter or any mean square estimation problem can be formulated and solved using those notions, the notion of vector space. So, I will now introduce you to this exciting topic from linear algebra called vector space. Maybe today this lecture and maybe couple of more lectures will be spent on that. Okay. This topic is abstract and does not require any background, but at the same time it requires good thinking. Okay. So, what I will do today, I will introduce you to this basic notions of, rather axioms of vector space, definitions and some properties and interesting things. Then this will continue till tomorrow. We will go into orthogonality, orthogonal decomposition of subspaces and all that. Okay, and then finally we will evaluate what is called orthogonal projection and all. Okay. Vector space. A vector space, actually we say vector space over a field. The field is another something which you do not know, possibly group, ring and field. There are various mathematical structures. One is called group. Group means a set of elements which have got only one operation. Okay, this is a group, only one operation and some properties. Then there is a ring. Ring has got set of elements with two operations, but one of the operation does not have the inverse. In another operation, inverse exists. Another operation, inverse does not exist. Like say polynomials. Polynomials, when if you add them, you still get a polynomial. Set of polynomial is closed. If you add, if you have one, I mean, what you say, group, ring, field, whatever it is, if you take any two element, apply any of the operation on that, you get another person from the same set. So, in the case of ring, there two operations are, say, ring of, say, this thing, polynomials. Set of polynomials is a ring. What are the two operations? Addition and multiplication. See, addition is simple. If you add two polynomial, you get another polynomial. So, it belongs to the set of polynomial. Addition has inverse, like negative of the polynomial, all those things are there. But multiplication of two polynomial, that is another operation. That also you get a polynomial. But that does not have inverse, because inverse of a polynomial is not a polynomial. 1 by that is not in the polynomial form. So, there is a ring. If it were a group, it would have only one operation with inverse and all. Ring means little more relaxed, one extra operation, but restricted does not have inverse. Then you have field. Two operations, both have inverse and satisfy all the properties of commutativity and other things. I am not getting into that. All real numbers, integers, all real numbers, complex numbers, they all form field under the usual notion of your this thing, addition, the addition of decimal number, multiplication of decimal real number, addition of real number, multiplication of real number, or complex number. Even your binary numbers, they form a field called modulo 2 field. You have got dot operations and plus operations and all those. Okay. Another example of ring, can you tell me? Ring, I give you an example of polynomial. Another example of rings, integers. If you take integer, you add two integer, you get another integer. You multiply two integer, you get another multiple. But inverse of an integer is not an integer. It does not exist in the set. Okay. Anyway, this mathematical structures finally generalize into another structure called vector space, where this vector space also will be a set. It will have two operations, okay, defined, but this vector space itself is defined over a field. Okay. Now, all those we do not need for this course. We will only, when for our purpose, we will be dealing with vector space defined over the field of real or complex numbers. That will only mean whenever I bring some constant scalar, that will be either a real number or a complex number. That is the only meaning. But I might write vector space defined over a field R or C, R for real numbers, C for complex numbers. In general, complex. Its only meaning for your consumption, only meaning is that all the scalars that will be handling in this treatment, that will be either real number if the vector space is defined over real, or is complex number if it is defined over C. Under that, vector space V over, this is called script R, means set of real numbers, or script C, this is called set of complex numbers, is what? It is a set of what? Elements, and this is what the troubles come. This is a set of elements, means just abstract elements. I do not know what they are physically. So, they are just symbols, and those symbols are called vectors. This has nothing to do with the usual notion of directional vector, that I vector, j vector, dot product, nothing. is a set of abstract elements. You can treat them as just symbols only, nothing else. They could represent anything depending on the case to case. You can have one kind of vector space, another vector space, depending on the particular vector space, and the symbols will assume some particular physical meaning, and that will change from context to context. So, here a set of elements called vectors. Elements, I am not writing everything, okay, you write sort of elements called vectors like this alpha, and I put an underscore here just to indicate that these elements of the vector space, or loosely they are the vectors, because after some time I will bring some scalar number, some real or complex value, and you will not be able to distinguish between which one is vector and which one belongs to this set and which one is a scalar. Just to distinguish, I am putting underscore as a mark, you understand. So, that you understand this is a vector, alpha, beta, gamma, dot 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 dot, could be infinity. So, that there are two operations on this. One, there exists mobile should be off, it gets recorded. I don't know whether my mobile is off though, it is not, so I should. Anyway, there exists a rule of vector addition, means this addition, mind you, please note, this addition is not the usual addition. I am borrowing the word addition, it is an abstract addition, symbolic addition, it has got nothing to do with our original or ordinary arithmetic addition or algebraic addition. I am just giving a name addition to it. I do not know what it is. Physically, what kind of operation I do not know, I do not care. It is just a name I am giving, one operation called addition. And for this also I will use the same symbol plus, but it is not again, it is a symbolic plus, abstract plus, nothing to do with the real plus. Okay, there is a rule of vector addition. What does it do? Like ordinary addition, what does it do? Take two numbers, give you another number. It also takes two vectors and give a result in the form of another vector belonging to this set. That is most important. It will not take you to something outside this set. Take any two, you apply the rule of addition. That is, so you can form a table of addition rule. On one axis alpha, beta, gamma, another is alpha, beta, gamma. So, alpha with alpha where, alpha with beta where, alpha with gamma where. So, you can form a table that way. Okay. It is just mapping alpha, beta, this pair it maps to where, alpha, gamma, this pair maps to where. So, actually in terms of set notation, it is V cross V. You know V cross V, this Cartesian product map to V. V cross V map to V that way. But I am writing in pure English. Vector addition, so that for all alpha, beta element of V, alpha plus beta, this is the symbolic addition. This is a vector, it is also element of V. Okay, number one, it satisfies some properties. This plus is, I have just said that this is one operation which takes two elements and gives you another element from this set only, but it should satisfy some property. What are the properties? One is commutativity, that is alpha plus beta equal to beta plus alpha. I am not writing for all alpha, this is true for any alpha, any beta belonging to V. I am not writing that, or maybe once I write for all alpha, beta element of V, this is true. Then associative, okay, you understand the meaning, na? First you apply the rule of addition on alpha, beta, whatever you get, that is an element of V. With that you apply, with that you take gamma, again apply rule of addition, you get something. You will get the same thing if you first take beta, gamma, the result you compare with alpha. These are simple, but next two are very important. There exists a unique, remember this linear algebra is key in all electrical engineering today, signal processing, control and all. There is a unique zero vector, I denote by 0, zero vector, this is a unique, only one element of V. So that when you take any alpha, beta, whatever, and take this fellow also and apply the rule of addition, you get back that guy only. So that for all alpha element of V, alpha and plus 0, that is this plus, symbolic plus, is alpha, and for any alpha or for alpha element of V, there exists a so called negative, symbolic negative, abstract negative version of alpha. There exists a minus alpha. Mind you, this minus alpha itself is the vector I am denoting. There exists a vector denoted by minus alpha. This minus is just a symbol, it is a dash element of V, so that when you add with this thing, you get back this fellow 0. So, this is called negative of alpha, denoted by minus alpha. Together is the denotation, minus alpha, dash alpha, or whatever. Okay, these 4. This on with respect to one operation called addition or abstract addition or vector addition or whatever. Okay, these 4 axioms. There is one more operation, that is scalar multiplication. B is scalar multiplication. Scalar will come from the field, either real number or complex number. Okay, that is why that R or C were there. You see, under A, everything was vector belonging to this V. There was no scalar here. This addition rule did not involve a scalar, but now vector will come. A scalar will come from there. What it does, it says, very loosely speaking, if alpha is element of V, C alpha element of V. Now, C alpha has no meaning here, because these are all abstract terms. It is not the 2 into 3. So, that is a formulate this, that there is a rule of scalar multiplication. Again, multiplication means abstract kind of multiplication, symbolic multiplication. What does it do? Take up any scalar number from this field, take up any vector. There is a rule by which works on them and give you another vector from this set, which I denote as C alpha. It is not in the usual sense of multiplication, it is abstract multiplication. So, for all alpha element of V and for all scalar C element of I am taking complex, same thing applies for real also. There is C alpha element of V. This is called the scalar multiple of alpha by C, just denoted by C alpha. Actually, some operation which takes C and alpha and give you a result. That result is denoted like C alpha. Do not imagine it is the usual sense of multiplying alpha by C. Do not extend that conventional notion of multiplication on that. C alpha is notational only, abstract. V. Again, it should satisfy some properties. The properties are simple. One is, if it is if C can be broken like this, C1, C2, alpha, C is a scalar, isn't it? Real or complex, so factorizable. C1, suppose factorize C1, C2. Then you will get the same thing if you take out say C2 first, take C2 and alpha, apply the rule, you get a vector from V, and on that you apply C1. Okay, physical, what is the meaning of this? Alpha and C2 you take, so you get a resulting vector by applying the rule of scalar multiplication. You denote it by C2 alpha. That vector and C1 you take, you get another vector again from V. These two are the same. Secondly, C1 plus C2 alpha, that is, if you add to scalar and then with that alpha you do, it will be same as if you take C1 alpha first, C2 alpha, and add by this addition rule. Mind you, here C1 plus this plus means for which plus? This is plus for the field, because this plus, see the interesting thing, this plus applied for what? The plus operation present in the field of scalars. Like this is a concrete plus, this plus for decimal real number or complex number. This plus is for vector plus, this plus defined here. You understand? I am using the same notation, but there is a difference. Okay. So, it says C1 plus C2, 5 plus 6, 11, alpha is what? 5 alpha, vector addition 6 alpha. So, see this, they are not the two same plus, symbolically they appear to be. Then, this was number 2. Number 3 is on the other hand, C the other way, alpha plus beta, which this is simple vector addition, alpha plus beta. That is, it is saying that you take two vectors alpha and beta, add them by the vector addition rule, then take multiplication with C. You would get the same thing if you have C alpha and C beta, two vector, and add it. And lastly, every field, whether it is complex number, real number, modulo 2, every field has one one element called identity element. Every field of numbers. If you don't want to get into field, you know 1, number 1 in real number 1, 1, 2, 3 at 1, or complex case also 1. That is the identity element. If you take that 1, this rule of multiplication says that 1 alpha should be equal to alpha itself. Rule should satisfy this. Then this is called a vector space V over the field of either real or complex number, depending on where you are taking the scalar from. We will assume vector space for complex in general, because complex takes care of real also. Okay. Certain things we see. What is scalar 0 times alpha? That none of these axioms told us. What is scalar 0 times alpha, isn't it? But how to prove it? Scalar 0 is 0 plus 0 into alpha, 0 plus 0, and we have got this thing, na? C1 plus C2 alpha is C1 alpha plus. This axiom is given to me, that I apply here. So 0 alpha plus 0 alpha, two vectors. So what is this vector? This when added to this gives you the same result. So by definition, there is a unique 0 with which only this happens, isn't it? It's such a vector. What was 0 vector? Such a vector which when added to somebody else gives you that somebody else only. These two things are same. That means this must be the 0 vector. See how I am using these axioms. Okay, I am not assuming anything else. So that means by that logic, this is 0 vector. So scalar 0 times any vector. Times means abstract times. It is not real multiplication anywhere. But this axiom suggests that scalar 0 and alpha, if you pick up, you get 0 vector of the vector space. On the other hand, if you have any scalar times 0 vector, then what you have? By the same logic, 0 vector can be written as 0 vector plus 0 vector, isn't it? Because what is 0 vector? 0 when added to anybody, get you the same body. 0 vector is what? When added to any x, gives you that x. Second, right? And now apply this axiom. The other one, what is the other one? This one. And again, this is such something that when added to say x gives you the x. So this must be 0 vector. Okay. Then suppose C alpha is given to be 0 vector. And C is non-zero. C alpha is given to be 0 vector and C is non-zero. C is not the 0 scalar. Then the only solution is alpha must be 0 vector. But how do you say that? Since C is non-zero, I can write this way, na? C alpha, this vector, I can multiply by C inverse. It is non-zero, so 1 by C exists here also. But just now I have proved any scalar times 0 vector is 0 vector. So C inverse 0 vector is 0 vector. Okay. And now take this axiom, C1 within bracket C2 means C1 C2 alpha. So C inverse C, there is 1, and then take this axiom, 1 alpha is alpha. See, mathematicians find out the minimum axioms necessary so that all other things come. You are following, na? I can bring C inverse inside, C inverse C, the scalar, for any scalar number 1 by C into C, there is 1 of the field, but 1 alpha is alpha. So by that logic, alpha is 0. If on the other hand there is given C non-zero, solution is alpha 0. On the other hand, if it is given that is given C non-zero, and suppose C alpha 0 and given alpha is not the 0 vector, then this should imply C equal to 0. That you can see easily by contradiction. Suppose C is non-zero. If C is non-zero, non-zero alpha 0 means by this theory alpha has to be 0, which contradicts. So, C has to be 0 that way, or you can have a direct proof. That proof you can work out. Okay. So, these are extra results that come from this, mind you, because if afterwards I write an equation, I find 0 alpha equal to 0, I have already proved. Do not extend your usual notion of multiplication and say 0 into something is 0, because it is not usual multiplication, usual addition. So, we really need these results, which look similar to our conventional business. Okay. Next, given a set of vectors, say alpha 1, alpha 2, dot dot dot, say finite number of vectors, alpha p element of V. This kind of combinations are called a typical linear combination. This is element of V. You agree or not? Because each term, scalar multiplication is an element of V, after addition also remains in V, so it is an element of V. This is called typical linear combination. Okay. Now, suppose let W be a subset of V, obviously it will be subset of V, which is set of all possible, please understand this, all possible linear combinations of alpha 1, alpha 2 dot dot alpha p. That means W typically has elements of this kind of form. W is a set. W is a set, and it set consists of what? You are giving these fixed vectors, just p number of vector. You are forming all kinds of linear combinations possible and collecting them. Each is a member of V also. That means this set W is a subset of V. About that there is no problem. Na? W is a subset of V, because every element of W is a linear combination which is an element of V. So, W is a subset of V. A set of what? Any element is of this kind of form, and is set of all possible such linear combinations, not just few. Then my claim is W also is a vector space by its own right. V is a space, within that W is a subset which is also vector space, and it is called a subspace of V. Then W, we will see this, it is called subspace of V. Why? Firstly, take any two element, suppose beta 1, beta 2 for all beta 1, beta 2 element of W. Beta 1 plus beta 2, what will be beta 1 plus beta 2? That also will be a linear combination, isn't it? That also will be a linear combination. Obviously, if you have C 1 alpha 1 plus this as a beta 1 and D 1 alpha 1, D 2 alpha 2 and you add the two, then using those axioms you can make C 1 alpha 1 and D 1 alpha 1 means within bracket C 1 plus D 1 into alpha 1 using those axioms. So, that is another linear combination. So, that means for any beta 1, beta 2, they are beta 1 plus beta 2 element of W. Any C beta 1 say element of W, isn't it? Any scalar C beta 1 means take this, multiply by a C. Okay, use those axioms, C into 1 vector 1 vector 1 vector means C on this, C on this, C on this, like that. You should get another linear combination, C1 alpha 1, C2 alpha 2. Using those axioms you can make within bracket CC1, within bracket CC2. It is another linear combination. So, that is part of W, very simple. Not only that, commutativity is very simple. Na? For addition, take any two beta 1, beta 1 plus beta 2, beta 2 plus beta 1, you get the same thing. Associativity also very obvious. 0 vector. If I take all the coefficients to be 0, I have already proved 0 times any vector is 0 vector. I did not prove it just for fun. This is a sequence I am going into. Scalar 0 times, linear combinations also include that particular case where all the coefficients are 0. That also is a linear combination. But I have already proved 0 times a vector is 0 vector. So all the 0 vector is 0 plus 0 plus 0 always be 0. That is the property of 0. So 0 exists. And then if you give me this, I take another linear combination where instead of C1 the scalar is minus C1, instead of C2 scalar is minus C2 dot dot dot. That is also a linear combination, part of W. But when you add the two, you get what? Suppose instead of this I take this. That also is part of W, isn't it? If this is part of W, this is also part of W. It is a linear combination. If you add the two, what do you get? You get 0, na? Using the axioms, you can take alpha 1 out and C1 and minus C1 within brackets, 0. 0 times a vector is 0, same everywhere, so 0. So that means for any element of W, its negative exists. Other properties of the scalar multiplication follow easily. Other property, scalar multiplication. What are the property? You take any element, multiply by a constant C. Resulting thing will be CC1 alpha 1, CC2 alpha, like that. Another linear combination. So part of W. Then if it is not that thing, C1, C2, if you multiply the entire thing by a product, say K1, K2, you will get the same thing as K1 separate and then K2 times this and then multiply by K1. Those are pretty trivial. Those axioms follow easily, I would say. There was one axiom C1 plus C2 times alpha is C1 alpha C2 alpha. So if you have K1 plus K2 times this, you can separate out. Or a K times one such combination, another such combination, you can separate out. K times this plus K times the other combination. And other one, 1 times this must be this. Obviously 1 into C1 1, 1 into C2 1, C2. Okay. By inspection only it is very clear. So W is a subspace. And then W is called subspace spanned by, we write this way, span of alpha 1 to alpha p. That means a subspace spanned by this means set of all possible linear combinations of alpha 1 to alpha p. I will give some examples, then you will see. Let me go through this little bit more. All real life beautiful examples will follow. No. There are so many other elements in V which are not covered. I will give an example. Why I just picked up alpha 1 to alpha p and taking their linear combinations. See, the logic only says that each combination is a part of V. Therefore, W also is a part of V. Whether W exhausts V or not, in some case it could, in some case, that I am not coming to yet. To tell you before, if W is a finite dimensional space, dimension I have not come to. Suppose that you know dimension. W is a finite dimensional space, dimension equal to P. They are so called linearly independent. That I have not proved all that. They form a basis in that case. But when did I say all that? I picked up arbitrarily P element. I do not know what is called dimension. P elements I am considering their span. Logic says W must be, you can say this way at the most.
So in this case it's like V is a plane and W is a line of
Like that. I put this way, this is better. Okay, it is called span. Next thing is this alpha 1 to alpha p. Is there any redundancy in them? Can one be written as a linear combination of the rest, or everybody is a kind of independent identity? That is the thing. If say given if no alpha I can be written as a lin comb, I am writing lin comb means linear combination of the rest, then this is then it is a linearly independent set, independent. Otherwise, that is, if at least one of them can be written as a linear combination of the rest, then it is linearly dependent. Okay. If not dependent, then independent, or if not independent, then dependent. It is a dependent set, linearly dependent. There are so many types of dependency, statistical dependence and also. Okay. Physical, this is a physical thing. None of the alpha I should be writable. Say alpha 1, you should not be able to write as something times alpha 2 plus something times alpha 3 plus dot dot something times alpha p. If you don't, I mean, alpha 1, I was trying to say that, okay, you can't write it like, something times alpha 2 and something alpha 3 up to alpha p. Even you don't have to take up to alpha 2 to alpha p, even less than that, say alpha 2 and alpha 3, even that will not work. That if you have that alpha 1 is a linear combination of alpha 2 and alpha 3, even that will not work, then it is dependent. Okay. Or alpha 1 is just a multiple of alpha 2, even then it will be dependent. Linear combination of the rest means you don't have to always take all the rest elements.
So you can have it 0.
Hey, that's okay. You can always assume a 0. How to test? Given this set, this is a pure English statement that, okay, if now, but how to really test it? This is an English statement that if none of them is expressible as a linear combination of the rest. This is a statement in English, but how to mathematically kind of, I mean, verify it? What is the mathematical condition for this or that? The mathematical condition is, suppose I form a linear equation, take a linear combination and equate this to 0 vector and want to find out the solution for C1, C2, Cp for which this is satisfied. Now, one solution all of you know is what? All 0 solution. Obviously, if C1 is 0, C2 is 0, Cp is 0, we already have seen 0 alpha is 0, 0 alpha 2 is 0, 0 alpha is 0 and 0 plus 0 plus. So, all 0 solution is a trivial solution, always exists. Now, if the only solution is C1 equal to C2 equal to dot dot equal to Cp equal to 0, scalar 0, then it is a Li set otherwise it is linearly dependent. We can see this way. Suppose, firstly, we have this satisfied, and we find some non-zero solutions for which also this is true. Suppose this equation is true for some non-zero values of C1 to Cp. At least some of them are non-zero. All may not have to be non-zero. So, suppose to start with, all are non-zero. Suppose in that case, I can just keep alpha 1 on the left hand side. C1 is non-zero, isn't it? So, you can say division by C1 is possible. Then the rest C2 alpha 2 plus Cp alpha p. So, that means this is a linear combination of the rest, isn't it? So, that means it is dependent when all the terms are 0, all the terms are non-zero. I am saying, so suppose a solution exists for which it is not that all, I mean all the terms are 0, it is a non-zero solution. Non-zero solution can be any kind. I am starting with the extreme case where every coefficient is non-zero. Then you can write like this. Now, suppose every coefficient is not non-zero, some are non-zero. So, this is 0, others are non-zero, then only this term will go. I can still write alpha 1 like that. Okay. Or only suppose only these two, C1 and C2 non-zero, others are 0, C3 0, C4 0, Cp 0. Even then, if C1 and C2 are non-zero, alpha 1 can be written in terms of alpha 2, still dependent. Suppose not even 2, only 1. So, C1 is non-zero, others are 0. In that case, 0 alpha 1, C1 alpha 1 0 and C1 non-zero. That means I have proved already alpha 1 must be 0. If alpha 1 is 0 vector in this set, still it is a linearly dependent set. Why? 0 vector can always be written as a linear combination of the rest. What kind of linear combination? 0 times alpha 2 plus 0 times alpha 3 plus dot 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 plus 0 times alpha p. Addition of a zero vector in a set makes the set dependent, because the zero fellow can be written in terms of the rest as a linear combination with zero coefficients. So, what does it show? That the moment you have any non-zero solution, either for all, with all non-zero, or part of them non-zero, or at least with one of them non-zero coming up, the set becomes dependent. Only when you have none of, and only when this is there, there is independent. Why? Because if with this it is not independent, that is, it is still dependent, that means I can find out, it is a contradiction actually, I can find out some non-zero solutions for this to express one element in terms of the rest. So, that means a non-zero solution of this will appear. Are you following me? See, the proof of this is this. I first started with non-zero possible solutions. I showed that any non-zero solution, if it exists where all the terms are non-zero, or part of the terms and part of the coefficients are non-zero, two coefficients only non-zero, or even one coefficient non-zero, it is a dependent set. What happens when this is the only solution? Then is it independent? Answer is, suppose in that case that you are saying this is the only solution and still it is not independent, you are saying, that means it is dependent, either independent or dependent, there is nothing third party, there is no third solution. Suppose it is dependent, that means any of the vector, say alpha 1, or could be anybody, start with, for example, say alpha 1. Alpha 1 should be expressible as a linear combination of some of the rest, if not all of the rest. So, that means I can put the terms together and make it equal to 0. Suppose alpha 1 is 2 alpha 1 plus 3 alpha 2 alpha 2 plus 3 alpha 3, and other terms are not present. I can write as alpha 1 minus 2 alpha 2 minus 3 alpha 3 equal to 0. So, that means 1 here, minus 2 here, minus 3 here equal to 0, but you are saying this is the only solution, isn't it? So, there is a contradiction. If this is the only solution and still it is dependent, then the contradiction will come, because I can form an equation here with some terms non-zero, because you are saying they are dependent. Out of the dependence, an equation will come up, because one is writable in terms of the rest, using that an equation like that will come up with non-zero terms, non-zero coefficient. That means that will contradict this. Okay. So, this is the test for linear independence. Now, coming to this, if you are considering the span of alpha 1 to alpha p, and additionally it is given alpha 1 to alpha p are linearly independent, that is, there is no redundancy in them, everybody is important, none can be written as a linear combination of the others. Okay. That is, everybody is important, mind you, that is why they are linearly independent. Then this set is called the basis, BASIS, basis of the space W. As such, they were spanning W. Any element of W was writable as a linear combination of the rest, because that is how W was formed. W consisted of all possible linear combinations of this. So, any element of W is a linear combination of this. But on top of that, if they are linearly independent, then this will be called the basis of W. If they are linearly independent, then the advantage, why we bothered about linear independence, I have in pure English told you that there is no redundancy and all that, everybody is important. But mathematically, you know, suppose you are forming a linear combination. Suppose alpha 1 to alpha p given to be Li, and you are forming a linear combination, say some beta element of, I am writing this way, beta element of W, I am writing this way, beta element of W as some kind of linear combination Cp alpha p, because any element of W is a linear combination of those. You have told me that they are linearly independent. Then my claim is these coefficients by which you are combining alpha 1 to alpha p to get beta, these coefficients are unique. Please understand this. If alpha 1 to alpha p are linearly independent, then these coefficients by which you are combining them to get a given beta of W, these coefficients are unique. That is, if I want to have something like this, this also true, that is, you find another set of coefficients d1, d2 up to dp, so that you linearly combine, you still get the same value beta, then my claim is this is not possible, C1 must be equal to d1, C2 must be equal to d2, Cp must be equal to dp, because this is linearly independent. How do I say that? Very simple. You subtract left beta from beta, you get 0, and here you subtract, using all those axioms you can write like that, C1 Okay. But you have told me this is a linearly independent set. So, if any linear, this is a linear combination of alpha 1 to alpha p. This is one coefficient, this is one coefficient, this is one coefficient. Please lift your head and see this. This is a linear combination of alpha 1 to alpha p. Left hand side has become equal to 0. You told me alpha 1 to alpha p linearly independent. This is a linear combination of alpha 1 to alpha p, that is equal to 0. So, only solution for them is this is 0, this is 0, this is 0, that means C1 equal to D1, C2 equal to D2, Cp equal to Dp. That is the advantage of linearly independent. So, if alpha 1 alpha p are spanning W and they are linearly independent, then I can come to this bold conclusion that any element of W can be written as a unique linear combination of alpha 1 to alpha p. You can have another set of linear combination coefficients are still giving you the same element. No, not possible. Every element of W has a unique representation, unique set of coefficients that can be used to combine alpha 1 to alpha p to get to that element. Conversely, if they are dependent, then there is nothing unique. Suppose alpha 1 to this also you can see alpha p, they are dependent, linearly dependent, and suppose you are having a beta as some C1 alpha 1 okay, but you are saying they are independent. That means, if I form a combination like D1 alpha 1 plus D2 alpha 2 plus dp alpha p equal to 0, you are telling me that all the solutions, I mean there exist non-zero solutions for D1 to dp or at least part of them, because they are dependent. That was the definition. Na? If you equal to 0, you may get non-zero solutions for all the coefficients or for part of the coefficients, for which also this is true. So, suppose I choose those coefficients and now I add, this still remains beta, but this becomes C1 plus D1 alpha 1 Cp plus dp alpha p. So, I get beta in terms of another set of coefficients, at least one of them is non-zero. So, one coefficient is new, and if it is true, instead of this I can take it 2d1, 2d2, 2dp still remains 0 vector and add again. So, you get C1 plus 2d1, Cp plus 2, that way there is infinite possibility. So, coefficients are not unique, they are unique if they are linearly independent. That is why stress on linear independence. So, if alpha 1 to alpha p are linearly independent and spanning a space W, then they will be called a basis for W, they are linearly dependent. In that case, any element of W is a unique linear combination of alpha 1 to alpha p. And now we will show that number p for W, that is a magic number. You can choose other basis also, I will show, but always you should have the same number p, and that is called the dimension of W. Alpha 1 to alpha p, how many? P. That p is some kind of a magic number. It does not depend on the choice of this alpha 1 to alpha p. From W I can pick up other fellows, say gamma 1, gamma 2, which also will be linearly independent, which will also span W. I will show how. But it will so happen total number will remain same, that will never cross p, and that p is called dimension. The dimension is independent of choice of basis. Basis can be many ways. I will show you how to construct basis. There are infinite ways of constructing basis, but number of basis element is fixed here. Mind you, we are dealing with finite dimensional vector spaces. In real life, many vector spaces are infinite dimensional, especially all the analog signals are when you deal with that time. We remember Fourier series and all, you have got summation going up to infinity. You will better understand what I am saying now, but at least that infinity is because we are in infinite dimensional spaces there. But in all these matrix, vectors, everything where things are digitized, they are all finite dimensional. We will see through some examples. I am just giving a brief hint. DSP is that way easier, because everything turns out to be, most of the things turn out to be in finite dimension. All orthogonal transforms basically they are, you define some new kind of basis, you get one transform. You say another kind of basis by which you linearly combine and get another sequence, get a sequence. You have one kind of transform by that name. That is, I will explain. I will give some examples and all. I am just telling you that is how basis transforms come actually. After all this, I will work out some examples for you. Otherwise, it is still remaining abstract. But before that, I have to still go somewhere far. Suppose I am in V. I take one alpha 1, and mind you, I am coming to dimension, and this proof purely a shortcut way without diluting anything mathematically. I am not diluting any rigor. No mathematician can challenge me as to I am making some weak foundation here and there. But These proofs are surely constructed by me for my students, so that I can quickly come at dimension without so many theorem or corollary and this and that. Okay. So, you just take notes here. Suppose I take an alpha 1 not equal to 0. 0 vector I will avoid, because 0 means dependence. Anywhere you add a 0, it becomes dependence. A non-zero alpha 1 I take out of V, no problem. Then I consider W 1 is what? Span of just this fellow only. Span of one element means, I told you span of alpha 1 to alpha b means set of all possible linear combinations. Here you have got one element. I cannot do anything in this 5 minutes. If there is only one element, then that means typically any element, typically what kind of linear combination? Just constant times alpha 1, C 1 alpha 1 or C alpha 1. So, just multiples of alpha 1, isn't it? Set of that is a vector space by the same thing. The W was a space that time for all possible linear combinations. So, this is a special case. You take any two multiples, add them, you get another multiple of alpha 1, that way, you know. So, this is subspace of V, fine. Say this subspace has 0 vector, because 0 times alpha, that also is part of it. In space, all multiples of alpha j, alpha 1. So, 0 times alpha 1 also is part of it, which is a 0 vector. Any vector space or subspace has to have the 0 vector, and 0 vector is unique for V. 0 is common. V or its subspace W, they all have the same 0. They intersect only at the 0. They intersect at the 0 by nu. Even if V has two defined subspaces W 1 and W 2 mutually disjoint, they have one thing common: 0 is unique. Each subspace has to have 0 vector, where vector space has to have a 0 vector, but 0 is unique for the mother space V. That means they intersect at 0. So, W 1. Then suppose I take a vector alpha 2, which is element of V and not element of W 1. That means I go outside W 1, I take a look at W 1, take anybody outside W 1, means not present of W 1, but present in V. Then my claim is alpha 1 alpha 2 Li linearly independent, isn't it? Very easily you can see alpha 1 and alpha 2, they are linearly independent. Why? C 1 alpha 1 plus C 2 alpha 2, if you get it to 0. Is it the only solution that C 1 and C 2 0, or non-zero solutions exist? Firstly, first suppose non-zero solution exists for C 1 C 2 both. So, that means you can write alpha 1 as some constant times alpha 2, or alpha 2 as some constant times alpha 1, but alpha 2 lying outside W 1. So, alpha 2 cannot be part of W 1. So, alpha 2 cannot be a multiple of alpha 1, because then that would have been part of W 1, isn't it? Alpha 2 is not contained in, so that is not possible, isn't it? It is like this, you know, on the, this is one axis spanned by, this one axis is spanned by one element. So, every element, every vector is just constant multiple times there, and I take another fellow this way, outside this in the bigger space in the plane lying, but outside. So, this can never be a multiple of this, they are pointing at defined, like that I am doing. So, alpha 2 both cannot be 0, both cannot be non-zero, because then alpha 1 is just minus some constant times alpha 2, or alpha 2 minus constant times alpha 1, means alpha 2 is part of W 1, which is a contradiction, not possible. Then is it possible to have C 2 0, C 1 non-zero? C 1 non-zero, C 2 0 means some non-zero into alpha 1 equal to 0, but that is not possible, because alpha 1 is non-zero vector. Some non-zero into alpha 1 0, that is not possible, na? Because alpha 1 is non-zero, that would mean alpha 1 0. Is it possible to have 0 here and non-zero here? Non-zero into alpha 2 equal to 0, that means alpha 2 0, but alpha 2 cannot be 0, because 0 vector has already part of W 1. So, alpha 2 is outside W 1, so alpha 2 cannot be 0. So, only possibility is C 1 and C 2 are 0. Okay. That means they are Li. So, I consider now bigger space. I will just 2-3 minutes stop. Alpha 1 alpha 2, this is V, this is still V, a linear combination of them. Okay. Linear combination of this is part of V. This was part of V, this is part of V, but you remember, you understand W1 content in W2, W1 content in W2. Okay, I think we stop here. You just go through this, refresh your mind, and then we meet on Thursday. We continue from here. Okay, we will arrive at dimension, give some example, then go for inner products, dot product, equivalent of dot product, more general notion of dot product called inner product. With that we will define orthogonality, orthogonal projection and all. I will need more lectures possibly, 3 more or 2.5 more lectures to cover all this. Soon I will do everything in the context of random variables. Vector space can be of any type, it will be basically in the vector space of random variables. 0 mean random variables. Okay then, bye, thank you.